In this video, we'll look at how systems of linear equations can be used to help us create a polynomial to go through certain points. I'll call this polynomial plotting. So given a certain set of points, how do we construct a polynomial that goes through those points? Let's say here, let me paste in an example. We want to find a polynomial of degree 2, that's a quadratic, whose graph goes through the points given. So a polynomial of degree 2 is uniquely determined by 3 points. In general, an nth degree polynomial is uniquely determined by n plus 1 points. So we want a quadratic, you give me 3 points, I'll give you a quadratic. So how do we use MATLAB to do this for us? Standard form of quadratic equations looks something like this. Y equals ax squared plus bx plus c. Those are the letters you're probably used to seeing in a quadratic equation, a, b, and c. So that's what's missing. So we need to find a, b, and c to make this work. And what do we mean by work? When we plug in x equals 1, we should get y equals 6. Just 6. We know those two numbers go together. So look at what happens when I write this down. I'm going to plug in, I'll move the y equals 6 to the right-hand side and plug in the x equals 1 on the left-hand side. Plug in x equals 1, and here's what we get. We get a times 1 squared plus b times 1 plus c equals, and then whatever the y value is. Let me move this over. The y value in this case is supposed to be 6. So 1 point gives us one equation. 1 point gives us one equation. We have 3 unknowns. We need 3 equations. That's why we need 3 points to create a second degree polynomial. Or simplifying, we get a plus b plus c equals 6. Now we can get another equation with a, b, and c in it by plugging in the other 2 points. Other 2 points to get more equations. Plug in x equals 2, and I'm supposed to get y equals 3, right? Let's just check. Yeah, 2, 3 was one of our pairs. So when I plug in 2, I should get 3 for the y value. In other words, ax squared, that's going to be 4a. So let's comment this out. 4a, because x squared is 4, plus b times x, so that's just 2x, 2b, sorry, we already know the value of x, we're plugging in for x, plus c equals 3. And from the other equation, from the last coordinate pair, we get, I gotta remember what it was 3 comma 2. So when I square the 3, I get 9. When I not square it, I get 3b plus c equals 2. Let's bring those all together and so we can look at them. 1, 2, 3. You won't have to do this every time. So what we've got now is putting them all together. We have a system of linear equations. Even though we're looking for a quadratic formula, we have linear equations because the squaring all happens to the x, and we know what x is. We get x's to plug in. So we can use MATLAB to solve this system of linear equations. Let's make our coefficient matrix 1, 1, 1, 4, 2, 1, and 9, 3, 1. By the way, let's look at this real quick. Run section and look at this A matrix we just made. Notice the right-hand column is all 1s. That's because all of these were C. There was never an x times C or anything else, right? C is just always by itself. The constant number is always there. So you're always going to have 1s there. That's like x to the 0 power. Here we have all the different x's. Remember our x's were 1, 2, and 3? Here they are, 1, 2, and 3. And in the first column, the squares of all of those, which makes sense because the first column is all the coefficients of A. That's all the x's squared. So you can start to see how we get a pattern here, which will be useful if you're making a larger program to do this with a higher degree polynomial. But for now, let's just keep going and we'll find our A, B, and C by creating an A and creating a B. Don't be fooled, the A and B aren't related to lowercase a and b. They're the ones from our matrix multiplication and matrix algebra series. So 6, 3, and 2. Don't forget to put those as a column vector. If you put it as a row vector, just transpose it, no big deal. And then we can solve by using our left-hand division, A backslash B. And let's run this and see what we get. Super fast. I kind of want to put a timer on that just to see what fraction of a second MATLAB took to do this. It would take a lot longer by hand, but MATLAB does it really quickly, and we get an answer for x: 1, -6, and 11. Now this is my A, B, and C, so we can create a polynomial with these coefficients. Now I don't want to hard code that into the program. I don't want to use 1, -6, and 11. I want to use the first element of x as a reference, the second element of x, and the third element of x. So here's what we're going to do. I'm going to create and plot it. Let's create lowercase x to be all my x values in my graph that I'm about to do. We'll go from 0 to, well, let's go negative also. I don't know. Well, I need to go at least as far as -6, but in general I wouldn't know that. So let's just pick -10 to 10, and we'll go, wait, I don't need to go as far as -6 because this isn't an x value. It's the value of my b coefficient. Oh well, that's fine. -10 to 10, and we'll count by, I don't know, 0.01. Okay, so I'm creating an x, and now I'm going to create my y, not hard coding in the 1, the -6, and 11. Instead, I'm going to use x1, right? That's my a coefficient, times x squared, dot squared, element by element, and then plus x2 squared. Nope, no squaring here. Just times x, that's lowercase x, plus x3. So I'm referring to coefficients indirectly. I'm using their references from capital X. And now I'm going to plot x and y. See if I can do this. Plot x, y. And hopefully this all works out really nicely. Run section. Cross your fingers. Oh, I don't need to see that. And I don't need to see that. Sure, I don't need to see that. We've already seen it. Okay, cross your fingers. What should we get? Let's think about that before we run it. We should get a quadratic, a picture of a quadratic that goes through the points 1, 6, 2, 3, and 3, 2. Oh, I definitely don't need to go as far as 10 and -10. Let's change it. No, let's not. Let's just run it and see what happens. So run section. Oh, that looks like a quadratic. Yay! I was holding my breath there for a bit. Let's see if it goes through the points. It's a little hard to see, but 1, 6, so that's around here. 2, 3, well, it's positive, and 3, 2. Okay, it's lower there. I definitely went too far by taking it to -10 and 10. Let's go to -1 and go up to 8. So because we were given the x values of interest, so we could use those. We could use those to bracket x for plotting. I just didn't do that. Run section, that's a little better. We can see that the 3 goes around to 2, the 2 goes around to 3, and 1 looks like it's just above the 5, so 1, 6 seems believable. All right, so that's how you can use systems of linear equations to solve for a polynomial that goes through a certain set of points. Good luck. If you need any help, please let me know. See you next time.